company that produces force and torque calibration equipment and adapters that are used all around the world. Last year, we actually celebrated our 100 years in business. 101 years is coming up just in a few weeks here. We are in the risk reduction business for force and torque calibration. And often we've had really some hard discussions with customers who may be either confused or frustrated or don't know about the importance of their measurements. But at the end of the day, we really know we've done our job if we can meet our purpose. And our purpose is to create a safer world by helping companies improve their force and torque measurement. So the presenter today is Henry Zumbrun. He is the president of Morehouse since for many years now, has worked at Morehouse, and he's now the president. Henry has a passion for measurement accuracy and reducing risk, all those risks that are associated with measurements. And these really impact our daily lives. And it's one thing I've learned from Henry over the last few months. It's just the far-reaching impact of these force measurements on everything from the planes we fly in, to the bridges we ride on, to the cars we drive in. So now I'm going to pass it over to Henry for the presentation.
Okay, yeah, Heather, thanks. Can everybody see the poll results?
Yes.
Okay, great. So
and do you want to turn on your video? I think the video is working now if you want to turn that on.
I can. You can see me. Everybody can see me scramble because for those that don't know, we're new to Cisco. This is a new platform. We were told, we made our decision based on the government using it. We've had a couple sessions here, poll results. Heather should be able to do the poll. For whatever reason, she cannot today. So I'm kind of doing that and doing this and that. But in any case, so if the poll doesn't go well, we can load the questions. Someone can say something. We set the first one at 38 minutes. Obviously, that's not going to happen for the next one. I'm going to try to tweak it the next time I pull up the next poll question. With that, I thank you for the introduction. As Heather said, I've been with Morehouse for a while. It's family business. We got into this business, those that were here last week, from the basic need of boilers blowing up, right? And developed the proving ring, which was at the time the greatest force measuring instrument in the world. Now that is not so much the case. There's load cells, there's other things. This particular course today, we covered some basics last week. What is calibration? Why is it important? And measurement traceability. And today we're going to talk about accuracy versus uncertainty, force calibration systems, and a measurement risk overview, which the measurement risk overview is probably the favorite portion of this, because putting together, that probability times impact. And if you're doing, we have some auditors here, and then it's detection, right? The other part is how can you detect it? Really just fundamentally good stuff all around as far as risk goes, and thinking about risk, not only, your global measurement risk, but your risk in general. If you're running a lab, assessing a lab, how can you help them be better? And that's hopefully there's some takeaways in this. You're spending an hour of your time with us. We certainly appreciate it. And I hope there are some good takeaways for everybody. Part of the outcomes, the hope is that the participant will be able to have knowledgeable discussions regarding force calibration basics. We're a little bit past that with this one, because this can be applied, a lot of this can be applied everywhere from what we're talking about today. And that starts with this general accuracy versus uncertainty, where we see specification sheet versus actual measurements. And there's a lot of good information out there. Probably my favorite, if you can go seek it, there's documents here that I want to briefly touch on. Scott Mims has one on the importance of definitions. Heather, I don't know if you can post that to the chat window if you can find it. It's just Google Scott Mims, the importance of definitions. Really, really good article. I encourage everybody to read. We're not talking about that today, but on my way in today, I started a new book, and those that know me, I read, I listen to books, I do all kinds of methods of digesting information. And the book I started today is Why Business People Speak Like Idiots. And I'm like, holy cow. We can apply this across our community of metrologists, beginners, and everybody else, right? Steve's shaking his head, yes. Absolutely. Because if we start throwing terms that are just, no one understands, and saying T.U.R, T.A.R, CMT, CMMC, CMC uncertainty parameter, calibration process uncertainty, calibration process measurement uncertainty, which is the true what it really is, but it would just shorten the word. I'd love to talk. However, whatever we talk about, it's important that we all are using the same fundamental definition of these topics. So little off kilter there, just wanted to go there a little bit. That is a great read for anybody. Hopefully Heather can put that in the chat. But we're going to talk about some basics. And this is a basic level. A lot of people confuse accuracy with uncertainty. This happens quite a bit. Well, how accurate is this device? Or you see a specification, or the auditors go out, you audit some labs, and they're using accuracy in place of uncertainty. They're saying, hey, I sent this to Morehouse. I asked for this to be 0.1% of applied. Morehouse told me it was 0.1% of applied. They used the method 5 from ANSI Z540.3 handbook, and I'm good. That's what I'm going to state on my certificate. That's what I'm going to state on my scope, right? Someone signs off on it. Okay, all good. Where's the stability? Where's all the other things that go into this? An accuracy statement alone is not to be substituted in lieu of uncertainty. So with that said, here definitions comes full around, right? Accuracy. This is per the VIM. The VIM is the International Vocabulary of Measurement. The closeness of agreement between a measured quantity value and the true quantity value of the measurand. Precision. Closeness of agreement between indications or measured quantity values obtained by replicate measurements on the same or similar objects under specified conditions. Very important here because, I've seen several definitions of accuracy where it says, hey, bias, you talk about some other things. When we talk about bias, a lot of times we're talking about measurement error. If you have something that's a nominal 10,000, instrument reads 9999, 9,999, that the bias would be 1 pound. So when we really talk about this, when we talk about accuracy, it kind of should combine some parts of precision in with that statement. And here, we'll go on. Everybody's probably seen this, and those that haven't, this is one of the cool things as far as, when we talk about high precision, high accuracy, or low bias, it's a dartboard. We have Olympics coming up. We're going to have, Summer Olympics. We're going to have archery. I don't ever see it on TV. I know it exists, though the best archers are the ones like Robin Hood and the other ones that, have high precision, high accuracy, and they can, somebody's going to be hung from the rope and they can hit the rope, fray it, split an arrow and stuff. That is really when we're talking about both good precision and good accuracy. Everything is centered. If you're playing a game of darts, you're hitting the bullseye. You're hitting triple 20s, triple 18s. That is, high accuracy, high precision. The next one we go here is high precision, which everything is clumped together really well, but low accuracy, we're further from our actual target. And then you have low precision, high accuracy, low bias, low precision, low accuracy with a scatter. So precision is a measure of spread. I like this one because graphically it shows us, right? We have our nominal value. I'm going to try to doodle here, something new here. We have our nominal value, like right here. Yeah, cool. I can doodle. Nominal value here. We have our bias. So if this were 10,000 pounds, this could be our nominal, and our bias was 999 here. Most people just look at this. But when we start looking at precision here, we're looking at the measure of that data. How well does that unit repeat? So if we just say accuracy, and I think I touched on this last week, there are manufacturers out there that will say, hey, I have a high reading, I have a low reading, and I'm going to take the average to report my accuracy. That tells you nothing about the repeatability condition, which is often precision of the instrument. And we know a lot of people do this. The saying is, I can have my head in an oven and my feet in an ice bath, and on average, I can feel fine. Very, very distinct differences if you have an instrument that a manufacturer has spec'd based on that high and low precision, that big scatter. Very, very, very different if looking at that in regards to repeatability and the other things. So accuracy, closeness of agreement between measured value and the true quantity value of what's being measured. I hope this graph does some. Here's another visualization. This one is with a one of our force gauges I used as an example, 500-pound force gauge. You can see that's what we want it to read. It's really reading like 499.8, something along that. And you can see the graph, the right here, visualize. There is anywhere in this, that device, based on this graph, could read probably anywhere from 498 to 501 pounds. So accuracy determined via calibration is not the same as uncertainty. An accurate measurement with large uncertainties is possible. That's the bottom statement here. I thought we had a polling question coming. It's probably coming. So here, again, we're looking at, I like this drawing. This one came out of Eurochem, where it looks like, you know, decreasing uncertainty, improving accuracy, and certainly includes all random effects. That's really what this is showing. You have some things here. Heather, do we have a poll question here, or am I off?
We have a poll question. It's in a couple more slides.
Okay, thanks. So talking about accuracy, talking about uncertainties, talking about accuracy, there's this concept called T.U.R, where Jerry Hayes, basically 1950s, Hayes and someone else with the Navy basically came up with this concept of like a 4-to-1, a 10-to-1 T.U.R. And it was a stopgap solution until better computing power was available, right? In the 50s and 60s, you're doing things, you're making measurements, and they wanted general rules. And they came up with this concept of a test accuracy ratio, which basically said, hey, if I'm calibrating this standard, I want to make sure my reference standard is at least 4 times better than that standard. A lot of people still use this today, and it's problematic. And it's not problematic when it's confined, meaning if we had an agreement, if I had an agreement with somebody else that's on this call today that said, hey, we're going to calibrate and it's going to be 4 times better than what your expected performance characteristic or your accuracy is, that could still work, right? But this picture right here shows that it doesn't work when we're talking about measurement traceability, which we talked about last week, which is each measurement contributing to the measurement uncertainty. So every stage here with this pen, each one of these has to contribute to the measurement uncertainty. And if we look at a T.U.R and build it out, we start here with process measurement or working standards, and then we're going 4-to-1 up. That's probably achievable. Another 4-to-1 up, probably achievable. And now we're getting at a 64-to-1, a 256-to-1, a 1024-to-1. That just does not happen. It's very, very rare. So in short burst, these T.U.Rs can work. There's several standards that are written, ASTM E74, that rely on it. But it is a confined approach that says, hey, we're going to be 4 times better, 5 times better, 10 times better, and we're going to build our pyramid out, and we're going to do it in the standard. So very different than general calibration, where you're looking for someone that's 4 times better. And if you think about it, they have to be 4 times better. Then who calibrates their stuff has to be 4 times better, and they have to be. As you can see by this pyramid, it just does not work. So, question, when you think of uncertainty, what one phrase or word would you use to describe it? I think this is our polling question, right, Heather?
This is just an open-ended question.
Okay, so I'm going to put the polling question up so I don't forget it. Anyway.
Polling question is in a few more slides.
Okay, so when you think of uncertainty, one phrase that you would use to describe it, uncertainty, value assigned to doubt, about the validity of an assigned calibration value. Document measurement uncertainties are required on calibration certificates to support metrological traceability. For those that know, NIST has performed some very good classes on uncertainty, and one of those polling questions was, what word do you most associate with uncertainty? Which, like 90-some% of that population, it was 100-some people, said doubt the validity. So that's why this slide is here, to further help explain that. But then we look at what really uncertainty. CMC, a lot of people shorten this, right? But if you look at the footnotes or you look at ILAC P14, CMC, what we're really talking about when they say CMC, a lot of times is they're talking about the CMC uncertainty parameter. So it's defined as a calibration and measurement capability defined by ILAC P14. For measurement uncertainty and calibration, the CMC uncertainty parameter includes the following standard uncertainty contributors, right? I like to call these 5 R's and an E. It's really easy to remember them that way. It includes repeatability. Remember, we were just looking at a slide with precision. It includes the resolution of the device. Lots of people now want to take this resolution out. Oh, we don't need it. If our standard deviation shows something with repeatability, we don't need resolution. ILAC P14 addresses this very, very well in saying, hey, if you have really, really good precise instruments that are showing 0 error or 0 deviation or spread, you will take that resolution into account. So why is that important? Those that some are following, some are new. So, setting that resolution or taking into account is important because as calibration providers or as users, we could set a coarse resolution and make everything perfect. So if I have a 100-pound, load cell that I'm using to weigh things, right? And at 0.01, I can detect changes on my scale. If I set my scale to 100.1 and I put things on and off, my uncertainty could get a lot better if I don't have any deviation when I calculate it. Therefore, resolution should kick in and say, hey, if I want to count by 0.1, I should add that to my uncertainty budget, right? If I want to count by 0.01 and I'm showing like half 0.05 deviation, maybe you can convince somebody that, okay, it's accounted for in that. What I am teaching today, or what I'm trying to say, is include it all, right? Do your uncertainty and then evaluate it and determine what's not significant, what is, what's not. And remember, several insignificant uncertainty contributors add up to major ones. So I'd like to put everything in the budget and then go from it for there. And if your uncertainty is a little bit bigger, does it really hurt if he's just a little bit bigger? I mean, our dead weight machine is 13 parts per million and we claim 16. And I do that because someone's going to come in and catch us somewhere and they're going to say, have you considered this or this? And I'm going to say no, right? I hope we have, but I may. Someone came in one time and said, have you considered stability? Yes, 0.2 parts per million over a 10-year period. It's been longer than 10 years since we built that machine. What's the drift on it now? Fortunately, NIST has a 50-year calibration interval on their dead weight machine, which they showed very little drift. So we think that holds. So in any case, when we did but again, a little bit more buffer goes a long way and gives you that, hey, if somebody comes in, hey, you just did a 10-year stability, and we say, okay, another 10 years is 0.4, we're still not over. Anyway, I regress. The next one, so it's the 5 R's and an E: reproducibility, reference standard uncertainty, reference standard stability, environmental factors, and there's another one that I throw out there, and it's just other. And other is your catch-all, right? That's where you can throw things like some specifications from load cells. You can throw some other things. What we don't want to see happen here for the general masses that are doing this, we don't want to see an accuracy spec negating all of this good metrologically sound advice. We don't want to see an accuracy spec used in lieu of all this. You need to do the testing. Force is very much determinant on the equipment and adapters that are used with it, and the machines need to be plumb, level, square, rigid, and have low torsion. Torsion is always present in all frames, but you can very much minimize it. So I sometimes you'll hear me say no torsion, but it should be low torsion, because I have yet to see something that you're trying to pull on or push on that doesn't have a little bit of a twist to it, especially if you're using threads. And most of the people that are pulling things in Force applications are using threads. Little tidbits in here. And if we look at that, what does this look like? This is a beginner course. We have some things online. Heather can post the link to that online. We have a CMC guidance document, CMC Uncertainty Excel guidance document that helps walk the users through doing all this. So it's a supplement to this learning, bit more advanced, but there's definitions and everything else that's in there. There's walks the user through it. And we also have a guidance document as to if someone wants to read as well. But if we do all of this, here's like everything. Here's R&R between techs. If we have more than one tech, we should do that. Repeatability, I have ASTM lower force limit in. This is this is test the reproducibility condition of the measurement. And then remember all these other error sources? I just threw them in so people can reference. This slide's going to be available for PDF. People can reference. This isn't the end all be all list of all the measurement errors, but it's a lot, right? Not using the right size plate. That's for truck scales, truck and aircraft scales. Bolting a load cell. If someone's unbolting and bolting it, there's going to be a difference with the torque specs. If I'm bolting it versus Heather bolting it, we're going to do it differently, right? I mean, I'm going to do the star pattern, do everything hand tight. Heather hasn't been trained yet. She's very, very smart. She'd probably pick up on it really quickly, but it's kind of, she may not do things, as she may use a different wrench, you know, all this. We're at the same building, so she's probably using the same wrench. However, if someone's sending us this from, let's say, California, they've unbolted a load cell, they've set us instructions on, hey, use the star pattern and bolt to 8 pound-feet of torque, right? But that doesn't, is it the same screws, the same base? You get into a lot of different things. So there's a lot of traction dynamometers, pin, S-beam misalignment. There's all kinds of stuff that's in our uncertainty course if anybody ever decides to take that, where we talk about all this stuff. So classify the type of uncertainty, A or B. Basically, the type A method of evaluation of uncertainty of measurement by statistical analysis. This would be what we were talking about earlier of the precision. If we take multiple measurements, take the standard deviation of it, that would be a type A. Other statistical methods I like a lot with Excel, you need to install the advanced pack normally, is you can do ANOVA, which is an analysis of variance. Really useful tool to testing, is it equipment, is it operators? You can do 1-factor, 2-factor. Again, this is more advanced. I just want to let people know it's there. But when you do that analysis of variance, you can compare things like, hey, I have 2 load cells. Which one is better? Same technician, both load cells, take the measurements. You can run that analysis of variance and statistically determine, is there a difference between both of my load cells? Really, really cool tool. So the other method, just basic, we're just typing type A, B. We're not going over distributions, everything else. Other assets is type B. Method of evaluation of uncertainty of measurement by means other than the statistical analysis of the series of observations. So here we're talking about things like history of parameter, other knowledge or process parameter, based on a specification, torque or load cell temperature effect. Maybe we're talking, you know, about the temperature effect of a load cell. Per 1 degree Celsius, I have an additional error of 0.0015% with a Morehouse shear web load cell. Hey, if you're operating at a temperature, our lab's calibrating it 23 plus or minus 1 degree. So you might get a cert from us that says 22.6. If you're operating at a temperature that's, say, 25 degrees, you need to put that in the budget. I mean, those little, like I said, the little things add up. If you're operating at 25 or 22.6, now your budget might be, hey, how much do I vary from that temperature spec? My lab, I'm controlling my lab within 0.1. Maybe I'm just going to use 1 degree, because the worst case I can see is me varying by, you know, it's 23.6 degrees. It's the highest temperature I'm going to see in my lab. You still need to put it in. It's just a lot smaller number. So force uncertainty, type A uncertainty contributors, things like the ASTM lower limit factor. That is a calibration standard for force instruments. I encourage everyone to use that standard for force because it is a legal document. There are committees that vote on it, as opposed to someone just saying, hey, do test this with 3-point calibration and verify it's within tolerance. That doesn't test for randomization characteristics. That does not test for reproducibility of the standard, where the ASTM uses a statistical method that basically randomizes the conditions of the loading to give the end user an expected performance of that device. You, as the end user, will then derate it using at different temperatures, different machines, everything else. But you can grab that in your uncertainty analysis if you follow this. If you follow what we're saying, the 5 R's and the E, and add the O for the other. Other type A, repeatability of the best existing device. These are documents, again, definitions. Best existing device is something that's out there that you may use for your laboratory that otherwise, I want to say, I don't have the definition in front of me, that would be probably the best you could achieve. So for force, if I don't have dead weight, a load cell comparator, the best existing device is an HBM right now is an HBM DMP 41 meter. It's about 50 grand, and a ultra precision shear web load cell from Morehouse, or there's a GmbH makes a fantastic load cell, though that's now you're going overseas. So in any case, they're both the best devices. If I have a dead weight machine and I want to do repeatability studies, reproducibility studies, I'm using that HBM with the very, 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 very high-end load cell, because my machine, I need something that can detect something. Hey, those that are in weighing, maybe you found like a really good artifact. It could be a rock, not the greatest, but I mean, if you have it and it's stable over history, that could be a good artifact as well. So a lot of stuff there. Type B, resolution made its way back. Reference standard resolution, I say if applicable, because in force, if you're using dead weights do not have any indication system, so you're going to rely on what you're testing. Reference standard uncertainty, reference standard stability, environmental factors, and other error sources. Now, stability can be a type A or type B. There's some other things in there, but just for the basics, typically we see stability as a type B, where you're comparing one cal to the next. NCSLI, I know it's their latest issue, has a great article on calibration drift and stability over time. Just fantastic. Highly recommend that if you haven't read it. So the note here is do not use, guess what? If you're doing an uncertainty budget properly, you probably don't need to use the manufacturer specification sheet with SEB, nonlinearity, or hysteresis. So here's a picture, again, from that chat window. Here's a picture of just down and dirty measurement uncertainty sheet. There's only 2 points here, but you can see the other point here, because this is a live example. When we do this in class, and we have people operate our machine. And we typically do 2 to 3 points, because watching someone do repeatability studies is really not the most exciting thing in the world. But, if you can talk and have people participate, it's good. And it's people's tolerance levels. So with that being said, we usually do, 2 to 3 points. This is one that came from a class where we did 2 points. What's important here is if you look at the expanded uncertainty that's calculated with all those things, the 5 R's, the E, the temperature specification, everything else, is look at these measurements. At capacity, at 2,000 pounds, this is our Morehouse PCM machine. At 2,000 pounds, we're at 0055. However, at 200 pounds, we're at 0.022. Quite a bit of difference, right? You see people just blindly throw out on scopes, hey, I'm accurate to 0.006% of full scale. That doesn't tell the end user the whole picture, because that doesn't tell you if they're going to do your device at any other point other than full scale, how good are they? So what this does is it does higher order fitting, but with 2 points, you're only going to get a 2 point. What this does is this will give you a formula then that you could put on your scope. Under the section, you can have a formula on the scope and you can use it, and it will tell you that, hey, you can run through that formula if you run through these numbers. If I run this through at 200 pounds, it's going to tell me that my uncertainty is going to be 0.022. Dealing with it'll do higher order math. That gets a little bit complicated because it's not as linear, right? When you have uncertainties that are maybe 0.02 at 10%, and then maybe your uncertainty is 0.04 at, that's going to decrease. Maybe your uncertainty is 0.01 at 50%, and then maybe it's 0.011 at 60%. Those type of things happen. And that's where there's some separate things to set the intercept and everything else. The important thing here, I'm going beyond the beginner. The important thing is when you're done with this formula right here, is that you run through all your points and make sure the calculated value of all these points is not less than what is the actual observed values through this. A little bit more advanced. But if we examine it, So if we examine the capability and what a reference CMC does to the calibration results, Morehouse versus accredited supplier, we have here expanded uncertainty, same 10K load cell. We're operating with a CMC uncertainty parameter of 0.0016% of applied. Our repeatability here about 0.57 because we know our uncertainty. The machine's plumb level square rigid. We have really tight precision on the load cell, and then we can compare this with another supplier. All they're doing is they're operating at 10K when they have their specification as like 0.04%, right? All they're doing here is taking the same things we are, trying to do the same calibration, and at the end of the day, we could put out a reference. We could put out a load cell someone sends us for cal. We could pull it out, send it to you with an expected performance of 0.41 pounds. The other supplier is going to send that same load cell out with a minimum of 4.03 pounds. So about 10 times lower than using secondary standards. And it's just the nature of it. Primary versus secondary. You can look at it any way you want. So Heather, I don't think oh, there we go.
We
so
got to our polling question. Yes.
Here's our poll question.
So as Henry's pulling this up, I want to mention a few things.
Yes, and as I'm pulling it up, it's unfortunately doing some things.
Okay, so as he's working on that, and if it doesn't work, we can do it in the chat. So as he's pulling that up,
people can answer
things. Okay, so I'm going to mention a few things. One is in the chat box. I did put the links. Can you go down a slide, Henry?
What's that?
Can you move down one slide?
To the question?
Yes.
I didn't want to because we're not animated. So it gives the answer. It gives the answer. So if people can answer it now, then we can talk about it.
So if you remember that picture with the high precision, low bias was the ideal scenario, then what is the second best scenario? So A would be the high precision, high bias, B would be the low precision, low bias, and C would be the low precision, high bias.
Yep. So the dartboard, I'm throwing darts at the dartboard. What is the second? What one is ideal? Okay, so it ended the polling. I can share the results here. Some are answering. Yep. So I can share the results here, I believe, right? Everybody see them?
Yes.
Okay. So we still had some here with no answer. So the second best in this scenario, what high precision, low bias is ideal. What is the second best? Second best, there's some people that are saying A, some people that are saying B. Ideally, one person saying C. Ideally here, if we look at this, I get this question a lot. Why? I'm going to vote for A, right? I do realize that B may be good, and there's a lot of people that have a lot more knowledge on processes and tweaking processes and adjusting them. Paul Reese wrote an excellent paper for NCSLI on this, by the way, if people are looking for additional reading. I'm going to go with A, and the reason I'm going to go with A is just in general is because if we have those tight groupings together, if our instrument is really repeatable, we can mathematically adjust, or most indicators we can reprogram the indicator, and if we do that, we can normally push A to the ideal state. Now B is a good answer, but our scatter, our repeatability condition is worse. So I get it would be ideal because you're not far off, but again, it depends on your tools and your measurements and what you can do and what you can adjust. And if we're going by definitions, definition of calibration in the VIM does not include adjustments. So you can get me on that one and say, hey, the VIM does not, but then you can, yeah. So anyway, not to regress. Force calibration systems. So we've covered accuracy and uncertainty. I talked a little about ASTM, and I'm going to talk a little more about it for those that don't know. Primary force standard is a deadweight force applied directly without intervening mechanisms such as levers, hydraulic multipliers, or the like, whose mass has been determined by comparison with reference standards traceable to national standards of mass. To be classified as a primary standard, the weights have to be determined within 0.005%. Compare that, they require the effects. When we talk about force systems and mass weights, they require the correction for the effects of local gravity, air buoyance, and air buoyancy. And there's a section in E74 6.1. Rolled, forged, or cast metal adjustment cavities should be closed by threaded plugs or suitable seals. External surfaces of weight shall have a roughness average, and it goes on. So that's basically saying, hey, I have a weight here. And for those that are auditors and the like, if you run into a company that's using mass weights to do force calibration, the main important thing here is to say, how are you correcting those weights for force, right? Are you correcting for local gravity? Are you correcting for air buoyancy? What are the error sources? Because air buoyancy is going to likely be, for those that do not know, air buoyancy comes out to be pretty typically the correction for air buoyancy. And sorry for my fat pen here that I chose. About 0.012% is usually the air buoyancy correction for force weights. You can adjust for gravity, for height, and some other things. And then gravity varies all over the world, right? So if I have a weight that I'm sending to Alaska versus Florida, it's going to be different. Here in right here in York, PA, when we adjust for our weights for force, it takes 1,000.7 pounds of mass to equal 1,000 pounds of force when we do the correction for local gravity. Denver is about 1,000.7, or Denver is 1,001.7, I believe. In any case, they're all over, they're all different, and it makes a big difference there. You talk about secondary standards. A secondary force standard is an instrument or mechanism, the calibration of which has been established by comparison with primary force standards. So in order to perform calibrations in accordance with E74, your force standard must be calibrated with primary standards. So what that is doing is it's just basically building that pyramid. If we're looking at it, we're saying, I'm not going to draw it. I'm just going to take my word for it. We're building a pyramid, going to start with 0.005, and then we're going to calibrate another standard, and then that standard is going to be used to calibrate another one, and so on. Here's some examples of different standards. There's a dead weight machine, primary standard dead weight machine. That's our automated machine. A secondary standard would be like a PCM with load cells used in it. We have like a tier 3, maybe a benchtop machine where we're calibrating, we're calibrating this stuff like dynamometers, we're calibrating crane scales, tension links. And then the end result of this, maybe it's a tier 4 where you're using it as a working standard to certify or verify a testing machine. And here's that pyramid that I wanted to draw. And what it really does here, this is the only situation where T.U.R can work, is it's built, right? This is our end user process measurement testing machine. The standard's basically saying, hey, to calibrate this, I need to have a standard that's calibrated this, that's 0.25%. And then in order to calibrate that standard, I need a standard that's 0.5, and it all starts with dead weight. It all starts here with dead weight primary standards. And that's all that it's built. You can't keep going and going and going. There's only 4 levels. There will only ever be 4 levels because this standard is written to support the E4 standard, which is the verification of the testing machines that are used to keep the bridges, cars, everything safe for you. Examples of load cells in machines. Here's, again, there's our UCM, there's a benchtop, there's a PCM. Just really easy. The primary standards calibrate these standards. These standards are then used to calibrate other instrumentation. So the right equipment for force, I said it, is going to minimize off-center loading, bending, and torsion. To do this, force machines must be plumb, level, square, rigid, and free of torsion. So all of the machines are designed. We're going to go through this section fairly quickly to get to risk. The right equipment for force is going to be plumb, exactly, true, or vertical. And there's a picture of the machine and the weights hanging. If the weights do not hang plumb and they go off to a side, we're going to have various error sources. The right equipment is going to be level, a device for establishing a horizontal line or plane by means of bubble in a liquid that shows adjustment to the horizontal by movement of the center of a slightly bowed glass tube. You can measure this lots of ways. The more level you have the machine, the better. We have adjustments on the feet. You can use a machinist level. You can use all kinds, as I said, you can use all kinds of things, bubble levels. This load cell in the specification basically says, hey, for a 1/16 of an inch, the error is 0.0003. So if I'm off level a little bit and, less than a 1/16 of an inch, I know I could have an additional error source that I'm going to put in my budget. And I was talking more advanced. I said I wasn't going to do that, but I see who's in the audience, and there's some takeaways I have for you. So square, force machine, this is about having 4 right angles, reduces the chances of misalignment. The bottom screw is aligned to the top beam to keep it as plumb as possible in this scenario. Rigid, this is one of our scale calibrators. If there's deflection all over in this beam or here, what's going to happen to my device on my scale? I'm going to have something that's slightly off center. So when we say rigid, we mean not flexible. If the loading surface starts to bend, all sorts of alignment errors can happen, which will impact the results. This usually comes up when you do your reproducibility, your R&R between techs. It will come up in that because you may get drastic numbers if you have a lot of bending in your system. Torsion, the action of twisting or the state of being twisted. Free of torsion means free of being twisted when forces are applied. When we first built this, there's a note at the bottom pictured right. We first built this machine. Our torsion, the error was like 0.3%, just way too large. And what was happening here is we have screws, and as things are twisting, as we try to pull things apart, they're twisting. Right? In compression, we didn't see it as much, but we did see it. So what we did is we designed this section here that I circled. We designed a mechanism, and those that want to see it can go online and pull down the PCM under products PCM. You can see it's a mechanism with bearings, cylindricals, sphericals, everything else to eliminate to lower the torsion. Right now, if we take 2 standards calibrated by dead weights, the torsion in this machine is going to be about 0.01%. We have not eliminated, but we've made it really, really low. So those that are using a transfer standard, something like this, it's an additional error component you have to deal with that's not found in dead weight. So take it for what it is. We've reduced it. That number of 0.01 is very, very low for a force machine. Most force machines have higher. When you're, like I said, 2-threaded rods, you want to pull, those threads have pitches. When you want to pull on something with a pitch, typically it wants to come undone. So here's our second polling question.
So
But what is Tier 2? But we've already answered it. So I'm not going to spend the time to do it. That's a Cisco WebEx. We need to be smarter and have an additional slide that has the answer. So Tier 2.
Would you like to pause for any questions here, Henry, or do you want to put them at the
No,
end?
we'll pause. Do we have? No, we'll go on a little bit more.
Okay.
We're going to measurement risk, and that's about 15 minutes. So, what questions? Yeah.
I just have a few questions, but we can hold them till the end if you'd like.
Okay. Yeah, let's hold them because I'm happy to answer them at the end because then we'll cut off the recording. So, measurement risk. Definitions. Again, the importance of definitions. ANSI NCSLI Z540.3 defines measurement decision risk, the probability that an incorrect decision will result from a measurement. ISO IC 17025 defines a decision rule as a rule that describes how measurement uncertainty is accounted for when stating conformity with a specified requirement. 2 things we need to consider. The importance of this picture here is to show that when we were talking and bring it all together, when we were talking about repeatability, and that was giving us the width of this graph, when you plot that graph and you put the tolerance lines on that graph, you can see how much of that graph hangs over. And that is really your measurement risk. So any part of this graph that hangs over is risk, right? So this picture right here says 68.26% is in, and 15.87 is out on the left, and 15.87 is out on the right. Sometimes you'll have some skewedness where it goes one way or the other. This is everything's reading perfect. It's just maybe the instrument's not repeatable. Maybe we're using that, the manufacturer's example where you had a high and a low measurement and you took the average and then you plotted it. So there's lots of different things to do here. When we talk about terms, we were talking about test accuracy ratio. That should be RIP ASAP, and that is a quote from Mr. Haynes himself, the one that invented it back in the 1950s. He, using that, better computing power is now available. I mean, the 1950s, right? Our cell phone today has more computing power than most things that were 20 years ago. And this definition came about all kinds. Scott Mims's paper is so good because there were all kinds of arguments on what goes in the denominator, what does this. This is it. The ANSI Z540.3 handbook and has the clearest definition of T.U.R for those that want to know. And the definition of test uncertainty ratio is the ratio of span of tolerance of the measurement quantity subject to calibration to twice the 95% expanded uncertainty of the measurement process used for calibration. Now, some people might say, well, the ANSI C540.3 standard, that's kind of going away. Well, there is a committee that's going to evaluate what needs to be brought forward and what doesn't. Those that say, hey, this standard is kind of defunct, I can say ILAC G8, the new ILAC G8 2019 also has a definition of test uncertainty ratio, which is almost the same definition. However, this version, take it from me, is a little bit better because it deals with not only two-sided tolerance, but one-sided. And when we say one-sided tolerance, that means where you just have a plus and not a minus, like plus something, or just one minus. A two-sided tolerance is basically saying, hey, I have an upper and lower specification here. And this definition deals with both of those scenarios where the ILAC G8 does not deal with them as well. So the definition, the one that I like the definition, I like ILAC P14 when it talks about short-term contributors. I'm putting this up as really a minimum, right? This denominator, if we go to ANSI Z540, it's going to say, hey, you're going to include the reference standard uncertainty in here. You're going to include the resolution of the device. You're going to include repeatability. Then it goes on to say stuff about transport, environmental conditions, a lot of other things that may or may not be specifically related to your instrument. So though we're teaching this today, know that this definition is not the end all be all. This definition, to me, is the very much minimum required when we look at ILAC P14 and kind of go with that guidance. Like I said, Z540.3 goes on and on about what goes in the denominator. So that's when we do these calculations today and I show these calculations, we're using this definition. So when we look at this versus a typical force lab, I showed a picture earlier with 10 times the uncertainty. T.U.R is really, really close to that. Where this one's is 22 to 1, and the one on the right, again, we don't have animation. The one on the right was 1 to 1. So therefore, same formula, same lab, or not same lab, same formula, different type of standard, primary versus secondary. These are both found in our lab. The secondary machine is over in our torque lab. We use it for experiments and some other things. Don't use it we do not use it to calibrate customers' instrumentation. Though when we do this, I mean, we start looking at a one-to-one T.U.R. and we look at specifically section 6.4.5, the equipment used for measurement shall be capable of achieving, right? So in regards to this, I mean, the question is, do you think it can, if you're using a one-to-one, is that good enough to achieve the desired result? Maybe it is, maybe it's not. In this example, the instrument was read to 10,000 pounds of force. Here's the one, T.U.R on the left is us, dead weights. Just think about this, dead weights. On the right, accredited calibration service provider. They may be better than this. I just using like a number like 0.4. And it depends on what you put in as tolerance. But look, each one is reading 10,000 pounds. A little bit of this graph is hanging over here. Nothing's really hanging over here when you're doing it with dead weights. Why? Because the largest uncertainty contributor in this example is the reference standard used for calibration. And if we move that number over, right, this is where you get into conformity assessment. We move that number over, move the location of the measurement. This formula, I love the standards that are written. What they fail to address a lot of the time is location, 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 just like real estate. You need to pay attention where that line falls. And there's good reasons for not paying attention to that. It's basically because if Morehouse or somebody else tells you that to generate 10,000 pounds of force, load it to 10,004, and if you're consistently doing that, that changes things. But general industry doesn't do that. General industry basically says, I have this device, I'm going to load it to 10,000 pounds of force, and I'm going to call it 10,000 pounds. I'm not going to say it read 10,004. I'm not going to use a curve or an adjustment to bring it back in. So when we look at this and that general expectation, and they're using the accuracy spec again, not using the uncertainty, using the accuracy spec, and you say, I want a conformity assessment, that other lab has to fail your device. They don't really have to fail it. They can call it an indeterminate pass or an indeterminate fail. They can give you the binary decision rules that G8 allows you to do, but that's not a pass. An indeterminate pass, an indeterminate fail is not a pass. And that people need to get with that and understand that. Now, ILAC G8 says you can fail when it's the tolerance plus the uncertainty that it's out, but that's all of your graph being out. So again, it comes down to risk, and we're going to go over risk and why that's important. But in this scenario, the risk goes from 4.55 to 34.47. And what that's saying is if I use this instrument and I calibrate other instruments, I have a 34.47% of being out of tolerance. I have a 34.47% chance that my device right now is out of tolerance. So this is how I like to present it. Those that have seen other things, I like this. If the larger the T.U.R, the more room you have. Here, large T.U.R, I can get out. I can put a lawn chair. I might even be able to, have those that know me know beer is near and dear to me. I could have put my cooler up, prop up my thing, all get out, have some microbrews with some friends, and I don't have to worry about denting the car next to me. And as opposed to a situation like this, the lab with the larger uncertainties, which is smaller, giving you less space to be in. Here, if it's winter time, which we're going through right now to date this webinar, try not to do that, but we're doing it. If my car's dirty, guess what? My pants are probably going to get dirty because I have to gradually get out of this car. I have to most likely suck it in from my beer drinking habit. And then I'm probably going to brush my pants or whatever. And if you're a female, you're probably going to brush your outfit or whatever on here as well. And chances are your clothing's going to get dirty, and it's going to be real inconvenient for you to open that door without denting it. And then when you come out at the end of the day, you're going to wonder if a new car beside you dented your door. So anyway, we've all experienced some of that. The person that gave me this, really near and dear, Mantech, a local manufacturing firm, she sent me this and said, hey, I loved your picture of, and I have the one to go with it because this is my parking scenario every day, and I wanted to share this with you. So, but 3 rules to lessen your measurement risk, and this is the stool. What happens to a stool when you only have 2 legs? It doesn't sit very well. What happens to a stool where you have 2.5 legs? Still doesn't sit well. It's not going to hold things very well at all. So the 3 rules, basic: know the right requirements. It's the first rule involves knowing what is needed to accomplish the task at hand. Rule number 2, choose the right equipment. Always choose measuring and test equipment that can achieve the measurement tolerance required. Have the right process. The last rule requires having a training program and proof of records to validate the individuals performing the calibration or using the equipment. So let's break it down. The first rule is knowing what you need to accomplish things. The more accurate the system, typically the higher the cost. We deal with that today. That's basically society. It's not all. There still are some good deals out there. There still are some very accurate systems that are less expensive than others. But in generalizing, this is what it is. I said the $50,000 meter, that's the high-end meter. The next meter down that I recommend is about $2,800. So pretty sharp decline. Again, that $2,800 meter may be really, really good for what you need to do. So know the rules, know the requirements. If the requirement is 0.1% of applied force and the stability of the device is 0.2% over a 1-year period, the device would need to have the calibration interval shortened. If you want to maintain it, every time you send it back to the supply and they're giving you the fail, not good, right? You can't continue to claim that uncertainty. You can't continue to claim I'm point, because as you go, maybe on day one, you're actually 0.1% of applied. But the end of that year, when the calibration provider is doing it again and calling it 0.2, am I really going out at the half year period? Am I going out at 3 months? Again, about risk. At some point, you're going out and you're passing that risk to the customer. What happens when rule number 1 isn't followed? People are on here. Anybody recognize this? This is the Texas BP refinery back in, I think, 2006. We have all kinds of stuff going on. What's interesting about this, this was caused by an idling diesel truck. And when things were leaking, that diesel truck ignited the whole place and it blew up, right? And when they did the root cause of it, they found out cost-cutting, production pressures, and failure to invest, lack of preventative maintenance and safety training, procedural workarounds. How many people have been in companies that have this? Procedural workarounds to compensate for the deteriorating equipment. The cost, 15 deaths, 180 injured, and $2 billion including lawsuits. And they found out that there was I think 1975 or 1976 outdated calibration certificate. It basically said something was falling when it was actually rising, and there was a hole. There was another safety hole that someone could peek in and see where the level was. And when they peeked in, that hole was all gunked up. It wasn't clean. So as to, I think we really could have spent about $1,000 to, have that stuff calibrated, checked. Maybe it's more than that, maybe a little less. I don't know. Whatever side of the fence you are, I think we can all agree that it was most likely under a few $1,000s, and a few $1,000s would have saved you $2 billion. Just doing some head math here, I think that's a couple thousand is less than $2 billion. I don't know. I got to pull out my calculator for that stuff. Anyway, choose the right equipment. Always choose measuring and test equipment that can achieve the measurement tolerance required. If you need to certify that an instrument is within a tolerance of 1%, you really can't say, oh, I'll just buy a standard that's 1%. We see a lot of people do that, right? Oh, a 1-to-1, that's good enough. Again, back to that risk formula when you put the reference standard in it. And my lecture here, several manufacturers do not understand measurement uncertainty and do not include the resolution or repeatability or the reference standard used to perform the calibration in their accuracy claims. They don't do it. There's a famous saying, I love the saying, achieve once, never repeated. Sometimes that goes into the claim. There's also a claim where manufacturers are really, really good and they do put it in. You don't know. You ask them. I sat down with a good colleague when I was presenting at a NIST function. I sat down and they're the one that told me they asked for an accuracy specification. Can I have the data? And the manufacturer gave them data that was outside of the tolerance, both high and low, and they told him they were using the average. Not going to mention the manufacturer there, but that is what happens. You don't know. So if you don't know, you can ask. Ask for test data. You're here. You can learn something. You can make your process a little bit different. And on most of these instruments, no reference standard in the world may lower risk if the instrument shows any bias. This is a situation of this. This is our old 8400 scale. This is an aircraft scale. It's a 60K aircraft scale. The instrument is repeatable with 10 pounds and has a resolution of 10 pounds, and the accuracy specification is 10 pounds. How is this possible? If everything in my system is perfect, my total risk is 12.1%. If I'm perfect. They're saying my specification is plus or minus 10 pounds. I'm saying I'm perfect and I still have 12% risk. So just another example. Know what you're buying, know the manufacturer, and then have the right process. You know, last rule requires having training program, proof of training records to validate an individual's performing the calibration or using the equipment. It is important to maintain and follow procedures that adequately support the end performance. There should be a process in place that ensures all aspects of the standards are being carefully satisfied in the calibration process. Use of proper adapters. We talked about that a little bit last week. It's so important for mechanical instrumentation. You get it some with electrical and test leads and other things, but really when you're talking about mechanical interaction, a soft material is going to produce mostly less output than a harder material. So adapters, orientation, alignment, all very, very important when it comes to force measurement. And you talk about the right processes. Here, those that don't know, the cranes, remember the cranes that were falling, and you try to root cause this, and you find out that there's a pin that they're supposed to put in this crane when they're disassembling it to make it more rigid. But it takes time. So guess what? People weren't putting the pin in. They weren't following the process. Heavy winds came. They blew this crane down. I think this was Seattle, I believe. Texas had it. For the longest time, we just heard on the news, crane, 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 and now you don't hear it. Wonder why? Because it takes those catastrophic failures for people to get out of their complacency and start revisiting their level of risk because they're worried. Usually there's financial, gains or losses on the line, lawsuits, whatnot. But we can do this. I mean, they could have followed this procedure. They could have done it. No one had to die. It's just really just stupid. Then we have this one. My favorite of all favorites of everything else, manufacturers promoting things. This is T.U.R. Customer says, I probably need to gray out the customer. Customer says they love it. Company's giving an example here of torque. This is a great way to calibrate. Now I can put torque on my bar and I can know that I have the right amount of torque. Well, anybody that knows anything about torque is lift force plus sine. And if you look at this picture, I mean, my angle calculation may be off for those that are saying, I'm saying that this is probably a 45 degree, maybe it's less, I don't know. I'm assuming 45 degree. But what happens if we look at this picture? We get an error, just calculated error, assuming it's 45 degrees, of 29%. So company here promoting this as a way to measure torque. We don't know the true length either, but they're promoting this as a good way to measure torque. And just by looking at this picture, I can tell you that the error, which is, this is a 0.1% of full-scale device, something like that. I can tell you that we're not even near 0.1, 0.2, whatever the claim is. We're at probably 29% error. But hey, before there wasn't any way to know how much torque was being applied, but now they can ensure they are meeting the required specifications. I don't want to trust anything that someone is making measurements on like this, because I'm sure maybe an engineer budgeted for maybe 1 or 5% error, as they tend to do. Those that know engineers build some things in. I'm quite sure they didn't budget for, 29% error. Again, very scary manufacturer promoting these things. Here's another one. We see this more in our world. We have competitors, they do. We like to all play by the same rules. But here, the E74 standard, the right procedures, basically says, hey, the verified range of forces shall not include forces outside the range of forces applied during calibration. And then we also have, in no case should the smallest force applied be below the lower force of the instrument as defined by 400 times the resolution for Class A verified range of force and 2,000 for Class AA. This customer right here assigned a verified range of forces, Class A lower limit of 192.3 pounds, where the sections of the standards are quite clear in 721 and 86 that this certificate should have said 500 because that's the first non-zero force point. So know what you're getting, understand what your calibration provider is doing, try to check it. A lot of people aren't going to see this. They're not going to know. They're not going to read the standard. They're going to assume who they're sending it for calibration is going to read the standard and do what the standard says. This is a case where they don't. So when evaluating measurements, what is always found in the denominator of expanded uncertainty? This poll will work.
Yes.
So we have that.
So as Henry pulls up this poll question, We are going to be coming to the end here soon. So if you do have questions, you can put them in the chat box. I see a few here already. And so I'm going to be getting to those at the end here. So as soon as Henry loads this poll, you'll see it under the chat box. There's a tab for polling, and I do see it's up now. So go ahead and answer A, B, C, or D in the polling question. When evaluating measurement risk, what is always found in the denominator for the expanded uncertainty? Either A, reference standard uncertainty, B, type B, uncertainty contributors, C, environmental factors, or D, resolution. And it looks like we have a few seconds here to finish out that polling question, and then Henry will show us what the answers are.
Yeah, and then we'll get to questions. We'll probably turn off the recording. I'll see. I can wait another 20 seconds. Some people are still answering, so we'll let them answer. Okay, and for those that answered, the correct answer is, do you see it now, Heather?
Not quite yet.
All right, I gotta click poll results. Why?
Now we see it, yes.
Yeah, so the correct answer is A. The reference standard uncertainty is always found in the denominator. Resolution, P14 talks about if we have that bit of standard deviation from repeatability, that maybe we don't need to put it in. So ANSI Z540.3 says we always need to put it in. Type B contributors, more than likely they may find their way in or not, but the thing was always. So we're always going to see that reference uncertainty. That's the one thing you're never going to avoid, right? Because you're looking at the measurement traceability, the unbroken documented chain of calibrations, each contributing to the measurement uncertainty. You're looking at that, and that's absolutely with the reference. So additional reading, we're going to get to questions. Additional reading, technical paper on adapters. Heather will send this out, the PDF of it out. Technical paper on uncertainty propagation, technical paper ASTM and ISO 73. I also had, that was in the chat window, hope you guys and gals could download the Scott Mims's paper. I just love that. I promote it everywhere because I think as a society, we're going through this yet again. People are trying to redefine that definition of T.U.R. yet again for their own agendas, right? And that's what we're at happening. We have task groups, we have other groups, they're just doing it. They came up with the definition in 2006, and around 2013, some of the ISO standards, some of the other ones say, maybe we don't want to put the resolution in. It kind of impacts us a bit. You know, how can we measure this? So anyway, I'm not giving that the full explanation that it needs, other than it's back around again. Definitions are back around again where people want to redefine them. So with that said, we're going to get to the questions.
Yep. So I have a few questions.